Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the lock-based protocol by the two-phase locking protocol, the implementation of locking, and finally the graph-based locking protocol. We about know that what is locking till now and when to acquire unlock and unlock and particular lock mode, that is in shared and exclusive lock mode. Now we have also seen that the ordering of locking and unlocking makes a schedule in a deadlock state or in an inconsistent result if we unlock too early or too later inside a schedule. Now the two-phase locking protocol ensures conflict serializability by producing a legal schedule in this way that the locks will be acquired in a stage and later in the shrinking stage it will unlock all the lock modes. Now, by ensured keyword, we are meaning that the locking protocol suggests that the serial schedule it is producing, it will be legal one, it will be conflict equivalent, and it will be a serial schedule. If all these three suggest and supports, then we can say that the schedule is legally ensuring conflict serializability. Now let us talk about this two-phase locking protocol. We have seen that unlocking too early on a data item queue we can result in an inconsistent state. After that, we have also seen that when we are having unlocked an item at the last of the transaction or delayed it until the transaction is not finished, so now we are having in a state that deadlock is occurring or deadlock is happening because one transaction is waiting for another one to get finished first and the another one also vice versa. So now what to do? Two-phase locking protocol gives us an idea that for each of the transactions as a schedule or as a complete schedule, there will be a growing phase on the schedule which will acquire all the locks on data item by every transaction. Now, after one point, every lock needs to be acquired by the transactions on a particular data item. After that, that point when we reach that acquiring locks is known as a lock point. So when we reach a lock point, then we are saying that after which point we cannot acquire any locks on any transactions furthermore. Now the phase will consist of unlocking of every data item. So in the growing phase, we will acquire every lock. In the shrinking phase, we will unlock every lock. We cannot have the unlocking phase into the growing one or any acquiring phase into the shrinking one. Now describe this two-phase locking protocol with an example. So what happens when we reach a deadlock situation in a transaction? We just roll back the transaction. When we roll back a schedule, any transaction that is causing the deadlock need to be rolled back to its previous state so that we can unrelease all the lock and then acquire it by another transaction to get rid of the deadlock situation. Now the cascading rollback, that means if T1 waits for T2, T2 waits for T1, doesn't work because one rollback will need another to rollback, which will lead to the schedule to be restarted again. Now what can we do? We can provide this two-phase locking protocol in this scenario. Now we will have this T3 and T4 as its result. Let us first define two transactions T3 and T4. Now we can see that this T3 and T4 is belonging to a two-phase locking protocol. Each of these transactions in this first phase, we are only acquiring the locks, and in here also we are only acquiring the locks. And in this phase, we are releasing the locks because it is this shrinking phase. So the growing phase and the shrinking phase is mentioned in two of these transactions. But these two are not deadlock free, because if we reach there that this write B, after that we need a lock SB, it will cause an deadlock to happen. So what will we can do to this transaction so that it can be deadlock free? We can produce, to make it in a schedule, a serial one with this two-phase locking protocol. Now, if we consider this schedule considering three transactions T1, T2, and T3, now look at this one, that both of these three maintain and growing and shrinking phase. The first one is having the growing phase, the shrinking phase. Second one growing and shrinking. The third one is only having the growing phase. Now we can see that this maintains the two-phase locking protocol and also this deadlock free. But we can say that when it reaches from this unlock A and goes with this lock SA, after that read A, when it will again perform this T1, then it will need that T2 and T3 to cascade rollback, because we cannot acquire an exclusive lock that we have on this unlock A on this unlock B. So now the cascading rollback option we need to provide for T2 and T3 while stepping from T1 to T3. So there is a position where we cannot acquire a two-phase locking protocol as our solution. Let us look at a more example. Now, the next one is about the strict two-phase locking protocol. When you use the keyword strict, because this two-phase locking protocol that means we are only not having the protocol on a two-phase, but also we are ensuring that if there is a transaction TY that has a particular exclusive lock on a data item A, so it has to acquire the lock on an exclusive mode until and unless TI produces in the committed state. That means if the transaction is in the uncommitted state, so it will acquire the exclusive lock on any data item that it has been acquired at any part of this time. So it is ensuring that if the data item is being acquired by the transaction and if it is not been completed, that means in somewhere in the later stage the transaction may need to write or read that particular data item. So we just cannot afford to release the lock before the transaction is committed, or any other transaction will start and have that lock as an exclusive on shared lock. So the restricted two-phase locking protocol tell us about that having the lock stayed in this two-phase locking protocol until and unless a transaction has been committed. So it is delayed until the transaction. Now there is another variation to our transaction protocol in a two-phase, that is a rigorous one. So when we talk about a rigorous one, then we are mentioning that if a transaction have any lock on a data item A, then it will not release the lock until and unless all the transaction has been committed. That means if there are TI, that is TI belongs to TN, so it needs to be committed, and after that only the TI can release a particular lock on data item A, whether it is in an exclusive or in shared mode. So now it is ensuring that the schedule which will include the transaction TI will be a serial schedule with the legal one and ensuring the conflict serializability. Now let us look at this example. Now say when this T1 and T2 has to be performed, first we need a shared lock on A1 data item, next on A2 data item the shared lock, on AN data item the shared lock. Now we need to write this A1, that means we need an exclusive lock on this transaction T1 on A1. Now we already have this shared lock on transaction T1 on the data item A1. So there is a mechanism that is very smooth and easy and reliable to use by this two-phase locking protocol, which ensures the conflict serializability. What is it? It is called the locking conversion. It has two phases. One is upgrading, another is downgrading. What do you mean by upgrading? If a lock has been acquired on a shared mode on a data item A1, then we can upgrade the lock to an exclusive mode if and only if anywhere in the transactions the data item need to be right on that particular data. Now what happens if the shared mode is available on A1? So we can acquire an exclusive mode on A1 by just lock converting into upgrading. Now what happens that if a right item lock on an exclusive lock is first needed by a transaction, and now we can have only the reading purpose on that data item, so we can downgrade it, that we can have only a shared lock for an exclusive lock. See, the changing from this shared to this exclusive is known as upgrading, and it requires no checking. But while the vice versa needs a checking because it cannot happen in every time. Say suppose that a data item has an exclusive mode lock for a particular transaction. Now it has been downgraded to a shared lock. Later somewhere the transaction again needs it for an exclusive lock. So it will cannot happen that the upgrade and downgrade are possibly running simultaneously. So we will can generate the downgrading as the time in the shrinking phase and the upgrading at the time in the growing phase for a particular schedule. Now we can also reach in an incomplete schedule if there are no transactions or incomplete granting permission for each of this locking and unlocking or upgrading or degrading based on this two-phase locking protocol. See, for the transaction T1 and T2, we are showing that read A1, that means we are having a shared lock on exclusive A1 data item. So we can have the shared lock and on data item by another transaction because SS is compatible to each other. We can have both the shared locks on the same data item from two different transactions at the same time. Same goes with A2 till now. So we have performed read A1, A2 for transaction 1 and 2. Now see, upon releasing this unlock phase, that is a two-phase locking protocol, because till now it is the growing phase for T1 and T2, and it is the shrinking phase for T2. And here we are all having the growing phase for T1. So now we are having an upgradation on this T1, that to shared lock to exclusive lock. But we know that when we are unlocking the shared lock, we are always having the shared lock on the transaction T1. So the upgrading doesn't require because already we are having the shared lock on A1, and we can just perform the exclusive lock by upgrading. See, the upgrading can only occur if the data item is required by the same transaction. So it cannot happen that read A1 is already there and now I want to upgrade it from another transaction T2. We need to unlock everyone before, and the other hand the transaction has been finished. So now my transaction T1 and T2 both has the shared lock and the T2 required for the upgrade. This cannot happen because S and X is incompatible to each other. So if there is no lock acquired by another transaction, only then one transaction can have upgraded its shared lock to the exclusive lock. and same with the downgradation. Now we will move to our next part of the section, that is implementation of locking. Till now we have described the locking protocol, that is a strict one, rigorous one on a general two-phase locking protocol. But how the locking is being maintained by a database management system. There is a lock manager who keeps tracks about all the transactions, their locks, granting of by the concurrent control manager, the release of these locks in a lock table. So now the lock manager maintains a log table for each of the transactions in a particular schedule, and schedule wise, table wise, and also transaction wise it maintains this record for the future use on a heuristic part or the commitment on the atomicity and durability of a schedule. Now we will see a log table which will contain 5 different data items. Say it. So first we need to check that if there for a particular data item, say for this 17, so we are first taking this 17. So if 17 is the one that we are checking, a transaction has a particular data item lock mode or not. If it is in the lock mode, then it will be added to the lock table as a linked list. So we can see that the lock table is a linked list where every data item is being linked to the other one by a pointer to it. So the pointer points to the next field that can be a data item or can be a null. For the last of this table, it will consist a null in the pointer field. See, for the data item 17, we are having this transaction 23 permission that is granted to us. So when we are having that the transaction is being permitted, it has been permitted for some particular lock. We are not going to the lock mode now. So now 17 is having T23. Now, if the new table is having no more locks, then we will just add one lock on a data item to it. Now, if 17 data item is needed further with this 123, so what happens? Say for it that it will acquired by unlock T1, T3 and waiting for a lock T2. So T2 is waiting for the data item 123 where T1 and T3 is having this 123 data item. So first one is when it is a new one, we will just add it to the linked list. If it is the next one on that particular data item, we will add a pointer to the data field that is next to it. Now say the 14 is arriving. So we can have the 14 as a new insertion. Say 14 has also been acquired and locked on T1. That means the transaction T1 can have that particular 123 data item on share on exclusive lock and also the particular data item 14 for this exclusive lock. Now say that T1 is waiting for this 14 and have granted, but T23 which has been acquired the data item 17 is waiting for the data item 14. Now there arrives 144. Now the data item 144 has been acquired the T3 lock that same 123 is having. Finally, the data item 1912. So the 1912 is being acquired the T23 lock too. So now using this lock table, we can see that which data items has been acquired to which lock, not the lock modes, and has been waiting for which locks. But this lock table is not showing us that which data item is being indexed with to which one. So here we are not using any index in this lock table. So we do not know that for go to the data item, we need to traverse the entire linked list to go for the particular data item. Say if we are going for this 144, we need to move to the 17, 123, 14, and finally 144. We cannot just go for indexed one in this lock table. Now, if a particular database has been deleted on a database lock, that means on the lock table, we will just delete that database entry and point that item to the null. So if 1912 is being deleted, we will point this data item to null because now my lock table is only having 17, 123, 14, and 144. So this is for the implementation on locking by a lock table. Now we will go to the next part, that is a graph-based locking protocol. As we know, when we talk about the two-phase locking protocol, that were not enough to solve the problem of deadlocking. It solved the problem of inconsistency though. But we need more information for our locking protocol to get established that the two-phase locking protocol issues. So now we will use another protocol that is known as a graph-based protocol. Here we will introduce each of these data items as the nodes to the graph, and we will add the transactions to the graph in such a way that it follows that the deadlocking situation will not arise at the most. Now see if a data item D containing on the sets of data item Di to Dn, and we need a precedence graph followed by these data items. That means if this di implies dj is happening, then we can say that di appears before dj. So the time quantum of di is less than the time quantum of dj. Now what we are signifying that for this database graph or the graph-based locking protocol, we need to introduce a tree protocol. So we are talking about a tree protocol that is a rooted tree. So when we are mentioning a tree protocol, that will need the data items and the transactions. So the first one, as we are saying that first one, the root of this data item can have any transaction to have a lock on that data item. So TI can get a lock on data item DI at the root node. Now at the next part, the data item TI can be locked by a transaction if it is parent node. That means if it is the leaf node, only locked by that particular transaction. Now if DJ is the child of DI, that means DI the parent of DJ, and TI has been acquired and lock on DI, then only TI can acquire and lock on DJ. Now the third one is if it wants to release by a particular transaction a data lock, it can do it just anytime, be in the root node, be in the leaf node, or any non-parent node. Now, if these steps are performed, the TI has locked on a data item DI and subsequently it followed by a release, then we cannot have this DI again locked for TI. So if TI is locked for DI followed by TI release DI, then we cannot followed by having TI lock for DI. So now if these four rules can be maintained, then we are defining the tree protocol to gain an exclusive lock on a particular data item so that we are not reaching in a deadlock consistency. Now all the legal schedules that we are performing under a tree protocol are always conflict serializable. Now to example this one, let us consider some protocols and some databases according to the transaction we will put into a graph. So for the first transaction, we can see it has acquired lock for B, E, D, then only have unlocked this B and unlocked this E. After that, it has locked for G and then unlock for D, and finally unlock for G. So after the transaction T1, all lock will be gathered for B, E, D, G and unlock them. Now let us look for the another one. Here we are considering a database item that is a child of another database item if the previous is preceding the others. Now look at this 2 and 3 problem. First one is having D and H, but unlock D and unlock H. So the order they have acquired the lock, they have unordered the lock. Now in T3, we have acquired B and D, but has released E and B. So it is in the reverse order, they have locked it. Now let us first draw this graph on which we can acquire these transactions. At the root of the node, we are having this A. So in these transactions, we are not anywhere mentioning A. So it is not our concern now. Now we can see at the first of T1 and T3, we are having to acquire lock B. So here now we are having B. Now after this B, we are having E also, and F also, and I also. Now after D, we can see there is H also. Now after H, we are having G. And here after E, we are having I. Now how can we build from this tree protocol that B is being the parent of D, E and F, D is being the parent of G and H, J and E of I. See here we are maintaining D of H relation, B of E relation and also B of G relation. So three relations here we are mentioning, and also we are having D of H relation. So now we are saying that this transactions follows this tree protocol. Now how to ensure that from this transaction based on this tree protocol, we can provide a conflict serializable schedule or not, which is free from every other problem. Now let us recall and based on this tree protocol, build this conflict serializable schedule. First, we are acquiring lock that is exclusive on B. After that, T1 is represented with a T2. That means T1 has been preceding to T2. So till here, we are maintaining the serializability. Now that we have unlocked D, so we can acquire it in transaction T1. Now we have unlocked this B and unlocked E. Now we have unlocked B, so we can acquire it by this T3. Now we are unlocking H on this T2. After that, we are having the lock of G here and also unlocking the D here. Now on T4, we will unlock the following. So after that, we have put in locks on this E. We are unlocking H from T2. Now we have acquired the lock X on G and unlock this D from this T1. After that, we can acquire the lock X on D because we have unlocked it from the transaction 1. and the lockex H has gone to be unlocked. Now it will unlock all this one for B and E in the transaction T3. Finally, it unlocks the lock G that it has acquired. So using this tree protocol that we have reached with a conflict serializable schedule with this T1, T2, T3 and T4. Now for tree protocol that we are talking about, this is producing the ensuring conflict serializability, but it does not assure the recoverability and cascadelessness. Now what happens that if there is any TI that being dependent on another transaction's commitment, that means we are performing a TI preceding TJ such that any value from TI is required to have this TJ to perform commit, or until and unless it is committed, that means has not unlocked all the data item, cannot further. So we are telling that TI is commit dependent on TJ. So TI will not proceed further until and unless TJ or any other transaction on which it is dependent has been committed, or any uncommitted transactions will be aborted by the concurrency control manager. Now, what is the advantage of this tree locking protocol? This tree protocol will give us that it will ensure the conflict serializability, thus no needs to roll back the item. So every time the tree protocol is maintaining the child-parent relationship, so we are maintaining no rollbacks are needed. But also one disadvantage with this tree protocol is associated, that is for every tree protocol, once the lock is being guaranteed by the data item. That means even if the data item is not accessed, we need to acquire a lock on the data item. Just like we have looked our data protocol, the lock item on A, C, H, J, F, I are not accessed in our transactions, but we have to acquire it and maintain it till the transaction commits. So there is an increased extra overhead of acquiring the lock which the data items are not accessed by the transactions. Well, this increased overhead is not a matter if we look at the ensuration of conflict serializability. But the main problem that dwells with this conflict serializability and tree locking protocol and two-phase locking protocol is that sometimes there are conflict serializable schedules that is possible for the tree locking protocol but the not two-phase locking protocol. And sometimes the two-phase locking protocol can produce the conflict serializability when the tree protocol is not able to do so. So thus, we will ensure this that which of the commands or this particular section demands which of this locking protocol. So it is upon the database designer to choose which locking protocol based on its database needs. So that is all for the implementation of locking, two-phase locking protocol and tree protocol for ensuring conflict serializability. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.